make me do it. All right, and up and down forever on both sides. And so what you find is, hey, this thing has a derivative everywhere, but the derivative function is not continuous. Okay. Now, Bonnie, do you see why I might have chosen 4/3 here? Yeah, so if this thing happened to be less than 1, I'd be in trouble just in making this differentiable. So it has to be bigger than 1 to make this differentiable. And it has to be less than 2 to get this to blow up. Yes, good. Excellent. No. No. It just needs to be a number between 1 and 2. Okay. Okay, so the answer is no. There are some things you can say. If you read the book, you'll see that, in fact, that even though the answer is no, it's not always continuous, f prime does always satisfy an intermediate value property. And not only that, but you can also say f has, it never has simple discontinuities. F prime has no simple discontinuities. They're always of the second kind if there are discontinuities. Okay. Okay, great. So this actually points out something that I guess it'd be worth mentioning, and that is we have a name for functions whose derivatives are continuous. Okay, because the derivatives aren't necessarily continuous, are they? So we call, this is not in your book, but it's terminology that's become very standard. We call a function f, we say that it is C1, a C1 function, if f prime exists and is continuous. And f prime is continuous. Okay? So this is an example of a function that's not a C1 function. Okay? This C is usually scripted, and it's supposed to remind you of the word continuous. Okay? So it has a continuous first derivative. All right? Similarly, we'll call a function ck if what? If it has how many derivatives? K derivatives, and the kth derivative is continuous. If kth derivative, which is sometimes written f with a parenthesis k, exists and is continuous. Okay. Now, you might ask yourself, well, how do I even know there are other functions that are, are there functions that are C1 but not C2? Or functions that are C2 but not C3, for instance? What do you think? Well, probably because I've got names for these things, right? How do you think I might construct such functions? Vary the exponent here. Okay, between 1 and 2, you'll get functions that are C0, those are continuous, C0 but not C1. Okay, and if this is between 2 and 3, you'll get functions that are C1 but not C2, etc. Okay, so you can construct whole classes of these things. All right, so I should mention C0 is a special name. This is continuous functions. And if you take derivatives many, many, many times, and if all the derivatives exist, we have a special name. Those are called C infinity functions. all derivatives exist. And we also have another name for C infinity functions. They're called, not surprisingly, smooth. So if you hear the term smooth in mathematics, it's actually a technical term. It means all the derivatives exist. Okay? And are continuous. Well, if they all exist, then the previous one is going to be, yeah, so they're clearly continuous. Yes? C0 just means continuous. No, this function is C0 because it's differentiable. I mean, because it is continuous. Well, it's continuous, so it makes it C0. It's not C1. It is C0, but it's a little more than just C0, but it certainly is still C0. The way we've made this definition, C3 functions are also C2 and C1 and C0. That's true, but but C0 refers to continuous function. Yeah. Okay. Excellent question. Great. So very good. What else can I say? So I said this mainly for culture because you'll hear this term, and many of you already have heard this term in other courses. What else can we say? Well, here's something that follows from the fact that f is a limit. So if f prime is a limit, well then I claim it follows from properties of limits of functions a lot of the rules that you're familiar with, right? Then you have the sum rule for limits of derivatives and product rule and the quotient rule. They all follow. And I'm not going to do these all. I'm just going to give you an example, just sort of see why this is true. What we're saying is you give me two functions. The derivative of a sum is a sum of the derivatives. I claim this follows from the fact that what? The limit of a sum is the sum of the limits. Thank you, Maya. So because the sum of a limit is the limit of a sum. Sums. Okay? Sum of limits, limit of the sums. Okay, let's see. Product. Well, what does this say? This say if you take the product of two things and you take their derivative, that's what? F, everybody should know this, f prime plus fg prime. Okay, where does this rule come from? Well, here's one way to think about it. Suppose I let h be f times g. H of x is f of x times g of x. Let me give you a picture proof, or picture motivation here. The book doesn't do this, but it's always helpful to have some picture in mind. Imagine this is the size, h is the size of a box, whose height and width are given by f and g. And as you increase the argument, which you might think of as time, this box is growing. Okay? So imagine at some time f of x, you have this particular width and this particular height, f of x, g of x. But then at some time a little later on, the height is f of t, and the width is g of t. Yes? So the rate of change of h would be looking at the area of the box, the change in the area of the box with respect to the change in time. Yes? But what is the change in the area of the box? Would you agree it's just this region here? But the change in the area of the box can be written in terms of two rectangles. Yes? So notice if then, what do you notice? You notice that h of t minus h of x is in